Hello again, everyone. As usual, we're starting with Brain Highways question. Pause the video, give yourself a minute, try to graph the function and answer the following question, and then play it again and check your graph. Let's first look closely to this function. Y equals half all to the power x plus 2, and then the whole function plus 2. What do we know about this function? We know for sure if the base is less than 1, then it's a decay, and the graph should look like this. Falling down from left to right approaches toward the x-axis. This x plus 2, when we add 2 to the x, it means the graph is going to be shift to the left 2 units. And then this plus 2, it means the graph is shifted 2 units up. Let's see how to graph such a function. As usual, we start by graphing the basic function before the translation. And in order to graph this function, we start by constructing a table of values for this given function. Let's see how. The table of values will be, those are the values of x. I'm assuming several values for x, -2, -1, 0, 1, and 2. And then we start substituting in the given function. Half to the power -2 is 4, and then half to the power -1 is 2. When x is equal 0, half to the power 0 is 1, and this is always the initial value or the y-intercept. When x is equal 1, half to the power 1 is half. Half to the power 2 is quarter. Let's see how to graph this function. I'm going to graph the original one before the translation. Okay, I'm using the blue one to graph half to the power x. -2 corresponds with y equals 4, -1 with 2, 0 with 1. Sorry, there is something wrong here. -1 with 2, it's here. 0 with -1, and then 1 with half, 2 and quarter. Join them with a smooth curve. This is the original basic function before the translation. But this is not the required function. The required one was half to the power x plus 2 plus 2. So as we said earlier, this is a combination of two translations. One horizontal 2 units and another one which is a vertical 2 units. So let's start by the horizontal one, 2 units. I'm shifting everything 2 units to the left. A question might occur here. Does it matter which translation to start with? No, it doesn't make any difference whether you translated it up or left first. Both will give you the final graph. I decided to start by the horizontal one by shifting everything 2 units to the left. So as usual, I'm shifting the y-intercept 2 units to the left. And then I'm going to graph my function. As said earlier, the translation never affects the asymptote and never affects the domain and the range. The horizontal translation doesn't affect the asymptote or the domain and range. The graph stays with the same asymptote, approaches to the same asymptote, which is the x-axis, and it has the same range above the x-axis. Y is greater than 0. But since we have another translation here, the second translation, plus 2, it means this new graph, the one in purple, is going to be shifted up 2 units. And as stated before, we would like to start by shifting the asymptote. If the x-axis was the asymptote this was the asymptote before, now I'm shifting it 2 units up, because the whole graph is going to be shifted up 2 units. And again, we have to start by this asymptote because it is like a boundary for me. It's a guideline. Now, I'm using the red one to shift the new graph, the one in purple, 2 units up. Let me repeat again. We started by the blue one, the basic. I will label it in order not to get confused. This one was the original one, half to the power x. And then we have the purple, which is half to the power x plus 2, shifted at 2 units. Now I'm using the red one to graph it with another translation. I'm translating the purple one 2 units up. Let's see how. This point will be shifted up 2 units. 1, 2 here. This one is 2 units up here. Sorry. This one will be shifted up 2 units. And then this one 2 units up. So those are the points I'm going to connect, the red ones. And the graph approaches toward the new asymptote. And this is actually the second part of the question. He's asking me about the new asymptote for the function after translation. It is y equals 2. This is the new asymptote after combining the two translations. What about the domain and range? Domain, as usual, all real numbers, while the range, the graph is all above this new asymptote, so the range y greater than 2. Hopefully, you could graph it with the same steps. Again, it doesn't make any difference either to start with the vertical or the horizontal. You should get the same graph. Let's now start our new topic for this video. It's 8.3 modeling with exponential functions, and our goal is to write models for exponential growth and decay. What does it mean to write models for exponential growth and decay? To write models, it means to build up your own function, to write your own equation. And in order to do this, we have a certain formula you can use. Let's look closely to this formula. A of t, which is the final amount, equals A times, between the brackets, 1 plus or minus r, all to the power t. What does it mean? A of t can be easily replaced by y, as we stated earlier. F of x, p of r, all those are just different notation for functions. In your book, you might see this one as replaced by y. And this is the final amount, and a is the initial amount. Let me give you an example to understand more those variables. If we're talking about investing money in a bank, you're supposed to deposit a certain amount of money, and this should be the initial amount. And you're expecting this money to be increased by a certain rate. This is the rate of increase over a period of time, which is t, so you can get the final amount. Again, if we're talking about investing money in a bank, you should put certain amounts, the initial one, the starting amount of money, the starting account in a bank, and this money will be increased by a certain rate, and in this case, this rate is a rate of increase, and this money will be increased over a period of time to get at the end a final amount of money. Is it the only kind of application to use exponential function n? No, we have another one which is also popular and familiar, to use exponential function in population. For example, if I'm recording the population of a certain country, I started recording with a certain number of population. This will be my initial amount. This is the initial population. And this number of population is increased with a certain rate over a period of time. Usually it's in years, because we're recording population by using t as number of years. And then the final amount will be the number of population after this number of years. What about this positive and negative? 1 plus r is used if we have a growth problem, if the number is increased, if the initial amount is increasing. Sometimes in some real life problems, as we are going to see during our tutorial, the number of money is decreasing. For example, if I'm paying installments in a certain rate, if I bought something with a certain value and this value is decreased over the time, then this is a decay problem, and we're using 1 minus r. about the rate of increase, it's usually given as a percent, but we have to convert it into decimal. We use it in the formula as decimal. So again, A of t, we can replace it by y. A is always the initial amount which you deposit, or the first recorded population. 1 plus r in case of growth problems. In decay problems, it will be 1 minus r. The r, which is always given as a percent, this is the rate of increase or the rate of decrease if it's a decay problem, and it's given in percent. You have to use it as decimal in the formula. You have to convert it into decimal and use it as a decimal. T is the number of time. Usually it might be years. In case of bacteria population, it might be seconds, hours, and so on. Let's see the first example in your book. Number 1. 1 year, a clothing company had $1.5 million in sales. So this was the initial amount. They had 1.5 million. In later years, the sales increased. So this is a growth problem. I'm going to use 1 plus r. By about 25% each year. As we said earlier, the rate is usually given as a percent. And this percent, in order to use it in the formula, should be converted into decimal. 25% is 0.25 as a decimal. So again, when you read the question carefully, 1.5, this is the initial value. This is my A. Later years, it increased. So my base here, the growth rate will be 1 plus r. And the rate is 25%, which is 0.25. Let's see the question here. Write an exponential growth model that represents the sales after t years. And he's telling me that the sales, the final is y. So let's first write the formula. Y equals the initial times the growth rate, 1 plus r, because it's a growth problem, to the power t, which is the time. Let's substitute now in the formula. Y, the final amount, is equal the initial, which is 1.5. 1 plus r, 1 plus 0.25 is 1.25 to the power t. I answered the first part of the question. He wants me to write the model in terms of t. He wants me to leave t as it is, as a variable. Number B, use the model to predict the sales after 8 years. Now t is 8 years. It means I'm using this model, my model, the one I wrote, and substituting t for 8. So y after 8 years will be 1.5 times 1.25 to the power 8. I'm replacing t by 8. By using calculator, you would find this is about $8.9 million. Let's see the next example. You buy a new computer for $1,500. The value y in dollars of the computer decreases by 40% each year. This is certainly a decay problem. I'm going to use the decay rate as 1 minus r. And it's actually, this is what we're facing now in the era of technology. Whenever you buy any device, after a few years, you find it a lot cheaper. So again, back to our problem. When we bought this new computer, this is the initial amount. This is the initial value A. I bought 1,500 to buy this device. And then the value of this computer decreased. So it's a decay problem. 40%, this is my R here. It's 40% as a percent. You have to use it in your problem as a decimal, 0.4. The first part of the question, again, he wants me to write an exponential decay model that represents the value of the computer. Let's see how. Y equals A times 1 minus R. I'm using 1 minus because it's a decay problem to the power T. Let's substitute now. The initial is 1,500. 1 minus R. 1 minus 0.4 is 0.6 to the power T. This is my model, the exponential decay model that represents this situation. Number B, use this model to estimate the value after 3 years. Now I'm substituting T for 3. I'm replacing t by 3 in my model. Y will be 1,500 times 0.6 to the power 3. Using the calculator, you would see that this is going to be $324, a lot cheaper. Now, the exponential function is a common topic in SAT, and the next two examples how to apply this formula in SAT questions. Let's read this together. You deposit 500 into a bank. For sure, this will be my initial value, 500, into a bank account that pays 3%. So R here is 3%, which is 0.03. Okay, this is the rate of the money. And then use the following to compute the amount in the account A. He wants me to use A as the final amount of money after 2 years. Here is T. T here is 2 years. So A, the final, is equal the initial 500 times 1 plus R, because it's a growth. The money is going to be increased, of course, if I'm investing in a bank. This is a growth problem. The amount of money should be increased. 1 plus 0.03 to the power 2. Can we find any of the choices here? Gives me the same answer. Of course, it's 500 times 1.03 to the power 2. It is choice number D. Let's move to the next example, another SAT question. It's in the official page of SAT. A researcher estimates the population of a city is increasing, again, growth problem, at an annual rate of 0.6%. Directly, whenever you see a percent, this is R. This is my growth rate, 0.6%. And as long as you see it as a decimal, doesn't mean it is in a decimal form. You still have to convert it. 0.6%, it means 0.6 over 100, which is in decimal form 0.006. If the current population, this is my A, this is my initial now, the current is 80,000. Which of the following expression appropriately models the population of the city after T years from now? So T stays T. Which one of those? Again, it's a growth problem because the population is increasing. So which one of those gives you the answer? Here it is. The initial times 1 plus the rate to the power T. The same formula we're using in this topic. That's it for today. Until we meet again, please do your homework, submit on time, and stay safe.